That looked painful. Hopefully, circular motion won't be that bad. Today's lesson is circular motion. Welcome back to another episode of Physics with Mr. McQueary. And today we're talking about when objects travel in a circle. Circle, circular motion. It's that simple. No way? Way. So, there are two forms of circular motion. One of them is called a uniform circular motion, which is basically when your speed does not change. Non-uniform circular motion is when your speed just does change. Luckily for us, we'll be dealing exclusively with uniform circular motion for the purposes of this course. A couple examples include the Earth moving around the sun. Maybe these bikers over here, if you've seen them at carnivals or circuses going around in that metal cage of a ball. Maybe it's a car going around a curve, or maybe a roundabout. Or maybe it's like SpongeBob and Patrick and you're just riding around in circles. These are all examples of uniform circular motion because their speed is not changing. One of the terms we're going to be familiarizing ourselves with today is called tangential velocity. And tangential velocity is a fancy way of saying moving in a circular motion. You notice that this arrow here is always pointing tangent or perpendicular to our circle. That arrow never goes on the side of the circle, and it doesn't get too far away from it either. It's tangent. First thing you do is look at the direction, okay? We've established that it goes tangent to our circle. And then you measure how fast you're moving. Those two things make up your tangential velocity. That makes up your direction and your magnitude. That's what those 2 points literally mean. The first point, direction. Second point, magnitude. So tangential velocity is a vector. Quick question here. Which way will the ball go? So that ball is attached to a string that's been going around in circles. Eventually, that string, for whatever reason, gets snapped. What direction will that ball travel? When the string breaks, the ball is still going to be going tangent to that circle because that's the way its velocity is pointing. So it's going to travel like number 3. Okay, it won't go flying out away from it. It won't curve back towards it. It'll keep going tangent to the direction it was going. So you see over here, okay, as it goes in circles, A would want to continue to go straight if there was no string holding it back. With that string not being there, it's going to follow its natural tendency. In a way, think about it, it's tied back to Newton's first law, the law of inertia. Another voting question here. This time, instead of a string, we have a ball that's going around a paper plate. When it flies off of that paper plate there, will it go in direction A, B, or C? Well, let's think about this. Just like with the string, there is that string that's holding it in that circular path. When that string is no longer present, it will snap off and it will go in the tangential path that it is wanting to travel because of its tangential velocity. Same thing with this. Since there's no longer that plate edge to keep it going in a circle, it will fly off tangent like path B. Tangential velocity, we have the basics down of it. Now we're talking about how to calculate magnitude, aka time to introduce some equations, okay? And there's a couple terms here that we've probably heard of before and one that's new. Velocity, we've heard that over and over again. It's basically how fast you're going with the direction. Your radius is going to be the distance between the center of that circle and wherever you are on the perimeter of that circle. Think back to math class. It'll be exactly the same. Period is probably one you haven't heard of before. Period is literally the time it takes to go in one complete revolution or one complete cycle. And we measure that in seconds. Radius we have in meters, and velocity is still going to be meters per second. All right, tangential velocity, now we have our magnitude here. Here's an example where we can use that. Noel Ryan, one of the most famous pitchers, back when they first started measuring speed by radar, could throw a baseball so hard that his entire forearm could travel forward in less than 1/10 of a second. We want to know how fast the baseball is leaving his hand. When the baseball leaves his hand, it should be moving with a tangential velocity. So that's the thing we're going to be solving for. We also want to underline our two given pieces of information here. The length of his forearm is going to act as our radius, and then the amount of time to travel that full circle will be our period length. You can use meters and seconds as hints when you're using these in word problems. Remember our guess method? We can still use it. Our given information, we've translated here to a radius and a period length. The unknown variable is our tangential velocity. Our equation is 2 pi r over t. We substitute, and then we solve. The velocity is roughly 44 meters per second, which I think if you look that up online, should be around 100 miles per hour. All right, so far we've had a situation like this where we've let go of the string, or the string has broken on us, and we've guessed what direction it's going to be moving. Now it's a simple question, either yes or no. Is that ball accelerating? Well, if the ball is accelerating, there must be a change in velocity. Okay, is there a change in velocity? Yes, there is. As that string, you can see here kind of a bird's eye view, as that string is being, with that ball is being twirled ahead, the velocity changes not because of the magnitude or the speed changes, but because the direction changes. And if you have a change in velocity, you must have acceleration. Here's our equation we use when determining the magnitude of acceleration, and we call that centripetal acceleration. The magnitude is defined by the velocity squared divided by the radius. Our radius is still the same one we used before, with meters as our unit, and velocity, just like our velocity we calculated earlier, will be in meters per second. Acceleration, as always, will be in meters per second squared. You'll notice that no matter where we are on that circle, the acceleration is always pointing towards the middle. So the direction is always going to be given to us just by drawing a picture. So is our acceleration constant? We said that velocity was not constant because direction changed. Acceleration has a magnitude and direction because it's a vector quantity. And even though the magnitude might be remaining constant, the direction certainly isn't. So no, the acceleration is not constant. Let's do a math problem together. The Wright Flyer, which was what the Wright brothers used at Kitty Hawk, turned with a tangential velocity of 47.5 meters per second. And the radius of said propeller was just over 1.25 meters. We want to figure out the centripetal acceleration that the propeller experienced. Okay. Let's underline our given information. Because it's expressly said that tangential velocity is 47.65 and that the radius is 1.3, this is pretty easy to plug into our given information. It's also pretty easy to plug in our unknown value, which is centripetal acceleration, because it expressly says it in the word problem itself. Let's go ahead and plug those in. The equation we can also use as v squared over r, and as you can see, we went ahead and substituted that in there for you with our given information, and we solved. That's a pretty incredible acceleration if you think about it. Those are some extreme numbers, but you need that in order to get the thrust to lift you off the ground, correct? Today's lesson has been a brief introduction to centripetal acceleration, to tangential velocity, and some of the very basic aspects of uniform circular motion. Till next time, see ya.